The next kind of problems we're going to look at, sort of some special problems where we look at what happens when we form an angle. So say we start here, and we decide to form an, whoops, this is Y. What we like to do is, they like to call this R, because you can almost think of the length from the origin to the end of that sort of ray or segment is like the radius of a circle. And the angle that was swept out, if you start the x-axis and go to here, the angle you've gone is theta. But then also they like to also talk about is this thing called the arc length. So if you can imagine, this line starts at the x-axis, and as it sweeps or moves up the angle theta, you can see how much distance we cover, and they call that the arc length, and it's indicated by the letter S. And there's actually an equation that says the arc length S turns out equals the radius times the angle. But very important for this formula, you have to plug in your angle as a radian measurement. The angle has to be in radians. If you're given a problem and you're told the angle is 40 degrees, the first thing you have to do is to convert 40 degrees into radians, and then you can plug it in this equation. So this is the equation for the arc length, but there's one more equation I like to use, and that's where sometimes they look at the area of this little segment here, the area swept out when you have an angle, and they have a little formula to calculate that area. In this case, the area is 1/2 r squared theta. And just so you know, for this angle here, the same rule applies. The angle has to be in radians for this formula to work correctly. So for instance, I'm looking at one of the problems on the review, and it says, for an arc length of 5 inches. So they're telling me the arc length is 5 inches, and an angle of 3 pi over 4. A lot of times in trig, we like to call angles theta. So they say an angle of 3 pi over 4. Then they say find the radius of the circle rounded to the nearest tenth. So they give us the arc length, they give us the angle, and they say, so what's the radius? Our equation is S equals R times theta. Well, in this case, I'm trying to solve for R. I'm trying to figure out R. So I'm going to go ahead, before I plug in numbers, I'm going to rearrange this equation. If I want to get R by itself, what do? I have to divide both sides by theta. And then I have this sort of new formula, R equals S theta. So now I should be able to plug in S, 5 inches, theta. Now be careful, this theta has to be in radians, this angle. What's my angle? 3 pi over 4 radians. So I can actually go and plug it in. Now this, they say round to the nearest tenth. So when they say round to the nearest tenth, they're basically saying at some point you're going to grab your calculator and do this calculation. Now here's another algebra problem. This is called a complex fraction. Let's go over here and do a quick review of how we would simplify this. Here we have a number over a fraction. Other times you might have a fraction over a fraction or whatever. Way back when you first learned to do this, it's simplest if we go ahead and make it a fraction over a fraction. So I'm going to change 5 to 5 over 1. Because what you learned a long time ago was the way to simplify this is you write the top fraction and then you multiply by the reciprocal of the bottom fraction. Reciprocal means you like flip the top and the bottom. So the reciprocal of 3 pi over 4 ends up being 4 over 3 pi. So this ends up being 20 over 3 pi. Now, I still want to go ahead. Now I can grab my calculator. I mean, if you can take your calculator and you can enter in these numbers and your calculator is smart enough to do it correctly, that's fine. But my calculator is old enough where really it's much easier if I do it like this. So 20 divided by 3 divided by pi, 2.12, but they said round it to the nearest tenth, 2.1 inch. And that's it. The radius is 2.1 inches. Now there's another problem that we can do, and this one says for a circle with diameter of 8 meters. All right, this is something different. So first of all, we've got a circle, diameter of 8 meters. Find the arc length, round to the nearest tenth, for an angle of let's do this one. So let's say you got a circle with a diameter of 8 meters. You've got an angle of 50 degrees, and what would the arc length be? How much would be sort of, what's the distance around the edge of the circle for this situation? Now a couple tricky things here. First of all, let's look at our equation. S equals r theta. R is the radius. It's interesting, they don't give me the radius, they give me a diameter. Hopefully you remember in a circle, there's the radius. If you go all the way across, that's a diameter. So the radius is always half the diameter. So if the diameter is 8, the radius is really 4. So I know r. Now I also need to know theta, but don't forget, for this equation to work properly, theta has to be in radians. And what was I given? 50 degrees. So I actually have to go off to the side and first of all convert this 50 degree angle into radians, and then I can plug it into my equation. Of course, we know already how to convert degrees into radians. So degrees on the top, degrees on the bottom, radians on the top, pi radians, 180 degrees. Basically, it's like 5 pi over 18. So now I think I actually have everything I need. I can finally use this formula. So S is 4 meters times 5 pi over 18 for my angle. At this point, there's no reason to try and simplify right now. I'm just going to crunch in the numbers. So 4 times 5 times pi divided by 18, 3.49, which is actually 3.5 meters. I believe that's correct. All right, so a couple different problems involving what normally is called this sort of like arc length equation. Now there's another problem that deals with the area, this equation. Let's go ahead and do that one as we wrap up this section. Here's what the problem says. Approximate to the nearest square foot the area of a 140-degree sector. So basically they're saying the angle's 140 degrees. In a circle of diameter 44 feet. Once again, they give us a diameter. Round to the nearest tenth. So basically, if you want to visualize it, once again, now we understand this, we realize R is 22 feet, right? Because our equation we're going to eventually use is 1/2 times r squared times theta. So we need the radius and then theta. Actually, we're going to need it in radians. I look up here, I've got it in degrees, so in a minute I'm going to have to convert again. So let's do that. Although if we just, sometimes it helps to draw a picture to visualize it. 140 degrees, 90's here, 180. 140 degrees is probably about right here. So they're saying this is like, this distance is 22 feet. We're going to try and find this area right here. All right, so let's convert our angle, because it has to be in radians. So my unit conversion, degrees on the bottom, radians on the top, pi over 180. So this can reduce to 14 and 18, and then if I divide it by 2, 7/9. So actually 7 pi over 9. So in a minute, I'm going to grab my calculator. So 1/2 r squared theta, 22 feet, you square that, times theta. I'm going to grab my calculator, see what this equals. 22 squared times 7 times pi divided by 9. I got this 2 here. I forgot what I did. 22 squared times 7 times pi divided by 9, then divided by 2. 26.867, which to multiply is 26.9. But I look at my answer, and that's not the answer. So let's do it again. That's why I've got the answer key here. 22 squared times 7 times pi divided by 9 divided by 2. All right, that looks better now. 591.317. .3 feet squared. All right, that looks more reasonable. All right, so not that hard. Now let's go back to some angles again. The next problems, they give you some angles, and for each angle they ask you to find the reference angle. So So the way these problems work is you have to be given an initial angle, and they say for this initial angle, find the reference angle. So a lot of times, if you see me do a diagram, I just call theta my initial angle like I normally do. And then a lot of times, I'll call theta sub r as my reference angle, especially when I'm drawing pictures, so you can just tell the difference. So what's the idea of reference angles? Well, here you go. Pretty straightforward. Here's an angle. The reference angle for this angle is the shortest or smallest angle back to the x-axis. So you're at some angle, and you want to know how far, what is the angle to get back to the x-axis. It could be the positive or the negative x-axis. So in this case, the initial angle and the reference angle are the same thing. However, what if this is my initial angle, and then I ask for the reference angle? Well, the shortest distance, or the smallest distance, or the smallest angle back to the x-axis, in this case, is this. Because this angle is much shorter than this angle. And the reference angle is always the smallest angle back to the x-axis. Maybe do one or two more. Well, if you have this angle down here, this is the fourth quadrant. There's your reference angle. Smallest, shortest angle back to the x-axis. Now, we sort of understand this. Let's figure out how we do these kinds of problems mathematically. So to give you a list of like 5 or 6 angles, and they want you to find their reference angle for each one. So let's see if we can just use a little common sense, and we can do some math if we need to. So the first one is if you're given an angle of negative 60 degrees, now there are a lot of problems in trig where the smartest, simplest thing you can do is actually draw a quick sketch or a quick picture of the angle, because once you see it, then it becomes very clear what the answer is, and these reference angles are a perfect case. Negative 60 degree angle, negative 90 is down here. There's negative 60 degrees. Now from just looking at this, what's the reference angle going to be? It's going to be 60 degrees. Now let me make a point. When we find reference angles are always positive. No matter which direction you have to move to get back to the x-axis, after you measure that distance of the angle, it's always a positive number. So that one's pretty straightforward. How about this next one? Once again, the easiest thing to do is to try and make a sketch of where this angle is, and that helps you to make sure that you're thinking about it correctly. So I know here's 180 degrees, here's 270 degrees. 210 is about 30 degrees past this, so maybe we'll say maybe that's a 210-degree angle. What's the reference angle? What's the shortest distance back to the x-axis? Hopefully, you see that's that right there, and it's pretty clear with these numbers. What's this angle here? Well, if this is 210, this is 180. Looks like the reference angle is 30 degrees. Let's do a couple maybe in radians, a little more interesting. So how about if we have a 5 pi over 4 angle, and we want to get the reference angle. Turns out 5 pi over 4 is like halfway in, right down the middle of the, oh, I'm wrong. Right down the middle of the third quadrant, because if this is 0, this is pi. So I'm looking at angles. There's a 5 pi over 4 angle. Now when I look at that picture, and if I'm asked to sketch or draw the reference angle, what would it be? Well, there's my reference angle. But what's the actual measurement? Now here's a place where you maybe need to do a little bit of math. So let me write here, this angle, let me write it out here, is 5 pi over 4. Now this angle is pi. So my reference angle, hopefully you can see, is just the difference, the angle between pi and pi over, or 5 pi over 4. So hopefully you see that this is the way I can calculate my reference angle. I take this whole angle and I subtract about this part, and that just leaves the reference angle. And once again, got to do a little bit of, in order to combine these, I need to convert this into a fraction. Pi is the same thing as 4 pi over 4. And now that I have a common denominator, I realize that my reference angle is pi over 4. All right, maybe do one last one of these. How about, well, I can't decide, so maybe I'll do both of them real quick. Because here's one that's different because your initial angle's negative. So here's one where for these reference angles, I think you'd be rather foolish if you don't just make a quick sketch of it, because that just makes sure you've got the right answer. Negative 7 pi over 6. So now we're going in the negative direction. I know pi over 6 is right here, or negative pi over 6. And then you move another pi over 6. So basically, there's negative 7 pi over 6. So here's my angle. What's my reference angle going to be? If we talk about negative angles, that's negative pi. So basically, you could think of the reference angle as the difference between 7 pi over 6 and pi. So really becomes this. Of course, I have to have the same denominator. Looks like the reference angle is pi over 6. Now, I haven't been checking my answers. I hope I haven't messed up on any of these. Guess I can check real quick. Yep. And then the last one quickly, because this one's a little different, where the angle's 15 pi over 4. Hopefully you can recognize now that this is at least one trip or maybe more around the unit circle. So we need to sort of reduce this down. So what we do is we sort of, I'm going to subtract out a 2 pi, which is one trip around the unit circle. 2 pi is the same as 8 pi over 4. So just so everybody knows, that's really 2 pi. So that leaves 7 pi over 4. And 7 pi over 4 is less than one trip around. So if I go try and 7 pi over 4, turns out it's right here. If that's my angle, what's my reference angle? How far is it all the way around this? It's 2 pi, right? So if I want to do it mathematically, my reference angle is all the way around minus seven pi over 4. Once again, subtracting fractions. 8 pi over 4 minus 7 pi over 4 looks like it's pi over 4. Looks like that would be the reference angle. All right. So let me stop now. We have one more video where we discuss a couple more kinds of angles, and then we're done with angles.